oscillations and waves. All right. We talk about waves. We're going to be basically talking about oscillations, sine waves. So we're going to be dealing with the pendulum, which is an example of simple harmonic motion. We'll also deal with the spring, which is also an example of simple harmonic motion. And we'll talk about waves in general and things like that. Okay, so we talk about simple harmonic motion. It's dealt with, we talked about springs earlier and the kinetic energy of springs, right? Because in a spring follows Hooke's law, meaning the more the force it takes to pull it down is proportional to the length it expands. So if we look at F and X, then where X is the distance the spring is expanded, the slope of this is K, or what we call the spring constant. And then the force is equal to technically minus Kx, because this force is pulling back. I mean, the force is pulling upwards. You pull down, the force of the spring is upwards, as far as that's concerned. So we got earlier into periodic motion as far as dealing with springs. We talked about energy. So a spring undergoes simple harmonic motion, meaning it's a sine or cosine. Sine, and we use the word omega t, where this is the amplitude. All right, so it would be, in this case of a pendulum, would be amplitude from the equilibrium, and as it goes in time, so this would be amplitude and this would be time graphed as far as that's concerned. So this is the peak, right? So the time from one to the other is the period, and the period is equal to 1 over the frequency. And using all right. That's how we get in there. So it's a sine or cosine. So it's the amplitude, peak to peak is the period, and then the frequency, and this will be in seconds. And that's what we have there. Okay. So that's a little bit on the start of that. That up for a minute, and let's go into we talked about kinetic and potential energy of a spring. So again, when I pull on it, the potential energy it contains, much like gravitational potential energy, mgh, this potential energy is 1/2 kx squared. Well, again, k is the spring constant, how much it takes. Basically, it's defined as how much it takes to extend it 1 meter, the number of newtons. So it'll be quite a bit. A meter is a lot. So generally, it's going to be a relatively large force. So this is the potential energy. The kinetic energy, as always, is 1/2 mv squared. And for a spring or a pendulum, this is what we call conserved. So the total energy will be the potential plus the kinetic. So I'll oscillate back and forth between potential kinetic, as far as that's concerned, right? Okay, so we've got then we define the maximum potential, so we extended a certain amount, all right? The maximum potential energy, so this one is normal. This is when you extend it down to its maximum, where x equals a, and the maximum potential energy will be given as 1/2 k a squared. So that maximum potential energy can be converted into kinetic energy. So as it oscillates, it'll be a maximum potential energy at this point, and actually when it comes back, and the maximum kinetic energy will be at the middle, at the equilibrium point. So it oscillates with maximum potential at either end and maximum kinetic energy in the middle. So this is max, KE max, right? And this would be PE max, given by that expression. All right, okay. Yep. Okay. All right. So now we're going to go into the periodic nature of all this. About the spring, and we'll start with the spring, and then move on to the pendulum. So the spring, again, is periodic motion, where this is the amplitude A, and the period of a spring is given by 2 pi m over k. Right? So it only depends on the spring the period depends on the spring constant of the spring and the mass that's hanging from it. So if I time the period, well, this one's pretty fast. The period is pretty short, but you can. It doesn't matter how long I extend it. It's just the period depends only on the mass that's hanging and the spring constant. Doesn't depend on how far I extend it down and that. Okay? So that's, and again, the frequency is 1 over the period. So this is the expression for the period for a spring. Let me do one example. Let's say I have a period, we have a mass of 100 grams, which is 0.1 kilograms, and we have a spring constant of, in this case, let's say, this is 200 grams, right? I'll also use what I have. And in this case, try and think what the spring constant would be. Let's see, it takes about 5 newtons. Let's say it's 100 newtons per meter, all right? Meaning if I put a 10 kilogram weight on this thing, it would extend it down 1 meter, which probably is close. All right, so then what would the frequency be? The period, all right, as we saw, the period is relatively quick, so I'm trying to estimate this, all right? Period is probably half a second. And so again, the period is time for up, down, back up every time. So probably about half a second. Well, let's see with this crude example. So that'd be 2 pi times the square root of 0.2 over 100. So we take that. Okay, that's 2 pi times 0.044. Okay. All right, and then times 6.28. We end up with t is about 0.28 seconds, which is probably pretty close to what I actually have. All right, so it's about 0.28 seconds. I was estimating this thing to be about half a second, but it's pretty good in that case. All right, so it's independent of the expansion. That's why spring clocks are so reliable, because the time is consistent as far as that's concerned. So that's for a spring, right? We can also express the amplitude then, and a graph is x, it's going to be a cosine omega t, where omega is 2 pi times the frequency. And again, we've had this before in rotational motion. This is in radians per second. So this is our expression of amplitude as a function of time based on this expression here. All right. So in this case, frequency is 1 over the period, which should be 1 over 2 pi times the square root of k over m. And they multiply that times 2 pi. 2 pi's cancel out, and omega is simply square root of k over m. So that's what omega would be in this case, the k over m. They all have 2 pi at all there at all. All right, so that's the case for the spring, right? Okay, moving on to the pendulum, and we have a similar thing here. So this is the expression for the spring. If we do a pendulum, I'm going to leave up the spring one just in case, for now. But a pendulum, right, is based on is the time it takes for it to come back, all right? So that's it there. Now, what we see is the period depends on the length. You can see the period is much shorter when it's short, and much longer when it's longer. Now, but we also notice is the period doesn't depend on the amplitude as long as the amplitude is relatively small, which can be up to quite a few degrees. And this is what actually Galileo discovered, watching the chandeliers oscillate in church when he was bored. He would notice that this was what happened, that the period had nothing to do with the amplitude. So if you look at this, for a pendulum, the relationship is period. Again, we have a 2 pi but instead of n and k, it's the length divided by g, where g is 9.8 meters per second squared. So that's the length in meters, and that's the example there. So let's do one example here, as far as that's concerned. Let's just pick this one. All right. So roughly half a meter, so 0.5. So it's a little over a second, I'd say about a second, as far as that's concerned. So what would it be? All right, so it would be period, would be 2 pi, 0.5 over 9.8. Now let's go back to our calculator. All right. Right, that's 2.2 pi times 0.23, right, times 6.28. We get t is about 1.4 seconds, which is pretty close to my crude estimation. So that's what we have for the period of the pendulum. Notice it depends only on length and g. Similar, just depends on two factors. Here it depends on g. Here there's no g, it just depends on the mass and the spring constant. It also doesn't matter what the mass you're hanging. Notice here it has nothing to do with the mass hanging. It only has to do with the length. And this is kind of have to do with, go back to gravity, is force and acceleration. All things accelerate at the same rate, regardless of the mass. We see the same thing here. So that's what you have for a pendulum. So that's the example there, spring and a pendulum. Okay. All right. Okay. Now we'll be talking about this later. All right, we're going to get a little bit in the wave motion. But we'll do this more when we talk about sound waves. But we'll get into this now, since it's part of chapter 11. We talk about waves, and we create a wave of some sort with some period. All right, there's going to be, if they're a real wave, it's going to be a distance. If it's oscillating, there will be a certain, if it's traveling down, then the relationship between speed of a wave, so speed is given by the frequency times the wavelength, when the wavelength is the distance between wave crests. So if you have the actual waves, so like water waves moving, they'll move at a certain speed. So depending on the wavelength between, or the distance between two crests, that'll define the frequency. That's how fast you cross together. So we'll get more into this later as far as that's concerned, particularly when we do sound waves and stuff. Because when we talk about speed of waves, we'll see for sound, as we saw earlier, speed of sound is 344 meters per second. And then we look at in chapter 20, later on, we'll see light has a speed of 3 times 10 to the 8th meters per second, or about 186,000 miles per second. So that's what we'll be dealing with going on there as far as that's concerned. All right. All right, so a couple more things here. I mean, this is a relatively brief chapter because a lot of this stuff we'll be doing later on, particularly when we get into light, refraction, diffraction, things like that. It'll be more important when we deal with it with light, which will be in 1102 if you take it in the second semester of this course. So, types of waves. So types of waves, and the best example, if we have a slinky of some sort, we have longitudinal, let's say compression waves, and transverse waves. And again, we'll talk about this later on, but right now we'll just leave it kind of straight, because when we talk about sound, sound is a compression wave, and light is a transverse wave. And we'll get into that later on, but the best way to illustrate this here would be just with the picture in the text showing on the top a transverse wave of a slinky where you shake it up and down and the wave is clearly seen on top there, where the wavelength is distance either trough to trough or crest to crest, as we call it. A compression wave is if you push it periodically, right? Push it back and forth, you get this wave that goes back and forth. In the top one, the motion of the particles is up and down, perpendicular to the direction of the wave. In the bottom case, are both in the same direction. So that's what we call transverse and compression waves. Again, sound, as we'll see, will be a compression wave. Light is a transverse wave. Now, a little bit about this also, when we get into water waves and stuff, a compression wave can travel through, and we have the three phases: a solid, a liquid, and a gas. I mean, sound, because air is a gas, that's why sound waves are compression waves, because a compression wave can because as the molecules vibrate back and forth, it can transmit in solid, a liquid, or a gas. Transverse waves can only travel through a solid. They can't because you have to bounce the molecules next to each other, and so that's not going to work. And if we see in geology, it's how we can determine what the interior of the Earth is based on earthquakes, because in an earthquake, an earthquake produces both kinds. The first one is called P wave, which is a primary, which is actually a compression wave, and the second wave produces also a secondary wave. So depending on how these are transmitted and received on the other side of the Earth, you can determine whether the core, the interior of the Earth, is solid or liquid. And that's how we understand the interior of the Earth entirely from earthquakes. All right? So that's a brief introduction to that part there. All right? So just briefly into that part. Again, we'll be doing a lot more of this when we get into sound waves and talk about light waves. Okay. Not going to get energy. Got that. Okay. Oh. Okay. All right, the last thing I want to do here is the concept of resonance. And you'll see this in the labs on the standing vibrating and sound tubes. An example might be, and we'll talk a lot more about this in a second, but this is the last section, and this is what we call standing waves. And if you look at the lab when we do it, we'll have the concept of resonance. All right? And the example here is if you have a wire fixed at both ends of length L, okay, and you pluck it, it will move up and down like so, right? This is a standing wave, so it's at both ends, and you can see if we were to extend this wave, it would be this long. So if this is L, the wavelength is actually going to be twice the length of that standing wave. This is what we call the first harmonic, F1. First harmonic. And this depends on a number of conditions, right? The tension in the wire, the length of the wire, the type of wire we have or string, as we can see in the lab when we do this. So this is that case. Okay. If the second one is if we have a second wave, all right? Second harmonic is going to be if we have one node in the middle, and there you have there. This is second, and here wavelength is just L. The third one would be, all right, in that case, the wavelength is 2/3 L. All right? So that's what we have there as far as those are concerned. Okay. Now as far as the frequency is concerned, this would be F1, say it's 100 hertz. So vibrating 100 hertz. F2 will be 2 times F1, or it'll be 200 hertz. F3 would be 3 times F1, and then it'd be 300 hertz. And that's what we have there. So this is resonance, and he's standing on a wire. So it vibrates. We have, in this case, and we can also see the number of nodes. This has one antinode. Antinode is the peak. So it has one antinode. I'll call it AN, and 0 nodes. This one has 2 antinodes and 1 node. F3, this had 1, 2, 3 antinodes, 1, 2, 2 nodes, and so on. So you can see the pattern here. Number of antinodes is equal to the harmonic. The number of nodes is 1 less than that. And the node is where you don't see any motion at all. And you can see that clear when we do the lab. So, all right, that's basically it as far as the lab is, as far as the section is concerned. And there's a little bit else in there, so look at the problems. That's chapter 11. That's 10 and 11 will be for the next test. And I'll do a review for that sometime next week for exam 4. Okay, have a good day.